Okay, guys, so in this little video, we're going to talk about processes and how to interact with them and what they can do. So, a process can, for example, access the file system, or it can issue system calls to the kernel. We're going to talk about what a system call is, but in a sense, a system call is a request for the kernel and asking kernel to do something with the hardware. So, maybe, for example, reading from some file to some buffer, or writing to some file, or opening a new socket towards some place in the network. Also, a process is running as a certain user, as we said, in both Unix and Windows most of the time. So it has the same permissions or the same access privileges as the user who has invoked it. It also maintains some open file descriptors. That means files that are open. It needs a file descriptor tracks of how far you've read into a file or how far you've written into a file, and it does certain bookkeeping around the file. That's what's packed into a file descriptor. So, for example, the standard input, the standard output, and standard error on every process is an open file descriptor. It can also send signals to other processes, or it, for example, ask the kernel to do some shared memory operation. Two processes might want to share part of memory. That's possible if they both agree on it, and then they can use a part where both processes can write and read at the same time. Now, on the video that I'm linking here, we talk a bit about the ps command, which lists processes, the lsof command for Linux that lists open files, and you can see how that can be useful, and the netstat command, which lists sockets, listening sockets, and other network related information on the video here. So click on it. Now, I'm sorry, I went back. I'll continue from here. Yes, sorry. So, continuing here. A process resides in memory and has a certain layout. So, there are various different layouts, according to the system that you're on, or the state of the program that it might be. And not all operating systems have the exact same layout, but they have they have similar characteristics, all of them. So there is a thing called the code of the process, that is the code currently being executed, every instruction as being executed. So if we have, for example, a very simple process that just adds two numbers that are in register 1, register B, and then writes a result on register C, and then exits. Their code would probably be just one add instruction, and then one ret, for example, instruction to return. So that part of the code would be on a completely different place than where the data that the process is manipulating is usually. There are different segments most of the time. So the executable code of a process with the data that the process is manipulating in real time reside in different segments in memory. Now, I'm mentioning here that, for example, .text usually contains the code of the process, like what I just described. That move instruction and that ret instruction would reside in the .text segment, and that's a bit counterintuitive, but in this case you need to remember that text means code. Okay. Then there are other segments, like, for example, .bss. This holds only uninitialized data. So if you write a program that has a global uninitialized variable, that variable will reside in the .bss segment. But if you initialize the data to that variable, if you say, for example, int foo equals 42, then that's not going to be in .bss. That's going to be in .data in that case. There is also, as you know, a process needs to have space to work with, and that's usually in the stack or in the heap. The stack exists there for every process, so they can it holds their local variables and their arguments as they're coming, because the arguments also need space. And the heap usually would be if you call something like malloc and allocate some space from the memory allocator of the system, the heap would give you back space on a different, again, segment of memory. Now, usually in the edges of these areas of memory are important control structures, like, for example, function return addresses. And this is, for example, the address to return to once the function has stopped executing. So you can imagine that if you can take control of that address to return to after the function has executed, you can take control of the process. Again, we try to see this under the scope of forensics, so we need to understand how programs are working in a legitimate way, and when programs are also broken by attackers, how does that broken program state kind of looks like. Now, just to give a visual example here of the layout, we can see, for example, we can imagine that the memory starts down here at the address 0 and goes all the way up to here, address 0xFFFF. Okay, and there might be some part of unused memory, and then we have a loaded process here, and it can have the .init, the .x, the read-only data segment, then you can have the data and BSS segment, and then you can have, for example, some space that can grow dynamically here by malloc to store things that have been allocated and requested with malloc, and then typically we have to free them with free. Then there might be some libraries that this process is using, and then after that is the stack that kind of grows the other way. Now, it's not always necessary that the stack will grow this way and then the heap will grow that way, and there will be mapped libraries in the middle. The mapped libraries might also be before the stack for some reason. But usually the stack grows the other way than the heap. And there have been, by the way, problems where it has been shown that at some points, although programmers take very good care of putting limits so that these things don't ride on top of each other, it has been possible in the past in operating systems to have the heap override part of the stack and so on. Now, you can see that, for example, here I'm writing, there's ESP, which is the stack pointer, and this is a pointer that always points to the top of the stack. Okay, so that's a stack pointer. And at the other side of the stack, there should be something that's called the base pointer. It's let's say the bottom of the stack, right? And this is the top of the stack. As you're adding more things, if you allocate, if you had the function now with one more variable, it would move the ESP further down, and that would allocate space for one more variable in your function. Then there might be like other things happening, operating system things, and then at some point in memory there is actually the kernel memory, right? That's isolated and not visible to the users, and you wouldn't be able to access directly these addresses up there. Now, as I said, in here, in these edges of this of the stack, for example, are values like the return address. So when this function again stopped executing, it would actually take the stack pointer back to the base pointer, and it would find over here the saved return address, and then it would try to go to that return address. So if we have managed to override somehow, then we can gain control of the execution of the program. Another thing we kind of need to understand is how processes are created in the beginning, right? So every process created by another process. We said that we have this init process, magical process that starts at the beginning of the system, and then this process creates more children, right? And that's process ID 1, and then the next one could be 2, 3, 4. They all don't have to be sequential. They could be like slightly randomized to prevent, an attacker predicting exactly the state of the system. But what usually is happening for historical reasons is that the way this happens in Unix is by what's called forking. So when you can imagine like a fork on the road, where now it's as if the same process duplicated itself. And that's exactly what Unix did in the beginning. So it actually copied the whole memory of the first process. It changed the process ID that was associated with it. But it got also things like the open file descriptors, for example, that was also duplicated. And then there is another thread of execution that happens there, and now these two are running on the system independently of each other. Now, if we could only do that, what good would be? We would only have clones of init there. So we also need a way to override the running image with another process, the image of a process that we actually want to run. And that is what exec does. So that is the combination of fork and exec. Exec overlays the new image of the program, of the executable, on top of the current memory, and initializes all these registers, like I mentioned before, the stack pointer and the base pointer, sets the instruction pointer to the correct address now, and starts execution of the new program image. Now, it doesn't have to be this way. There is nothing that forces us to always copy a program first and then overlay the image with a new one. If we don't want to. This has happened in Unix for historical reasons. But for example, on Windows, they had an approach more similar to the newer facilities available in Linux, something like clone. So you just say which executable you're going to run, and that is loaded directly. You don't really duplicate the image first. It has slightly different semantics. It might end up doing the same thing, but the semantics matter, because when you copy things from process A to process B, it has been a source of many bugs where things were copied that shouldn't have been before the new process was overlaid on top of it. Now, we said that the code is actually stored on the .text segment, and you can kind of treat even program instructions as just some sort of text. Okay, most of it is not really readable in nice ASCII or something, but parts of it might be readable. So in this video, you can go and see how a hello world program looks like. You can imagine that a hello world program has somewhere the string hello world in it to be printed. And indeed, if you examine the binary of the program, if you compile it and examine the binary of the program, you will see in there the string somewhere hello world. So just by that, now you kind of have an idea of what this program could be, just by looking at the binary with strings, for example, or with your favorite editor. This is generally a good approach. I do when I want to have an unknown executable. It's very passive. You don't really run the executable. You can just look at what strings it contains and try to make sense of what this program does just by this static data. Of course, there's no guarantee that just because this static data is in there, that's what the program does. You shouldn't do only that. Anyway, watch this video. Now, okay, we said we can examine, just run strings on it. What else can we do? Well, if we have a running program now somewhere in the system, and we still want to infer what it is doing, we can, for example, using the commands that we said before, we can do lsof, and we can see the open files. Well, we could see what files it has open, right? We can see if it talks to any network sockets and where it is connected to. We can see, again, as I just mentioned, the text. Another fantastic facility that we have is seeing what types of system calls it requests from the kernel. So we can run it under an introspector that shows us whenever a system call is made, a tracer, whenever a system call is made, it prints that on the console. So it will tell us the program right now asked to read 4 bytes from this open file descriptor, or it said that it wants to write these 16 bytes on that open file descriptor. And the program continuously interacts with the kernel to do anything really useful. System calls, we mentioned them again before, but some examples are, again, open, read, close, even get some entropy from from the system, or get a source of random numbers. That could be a system call, and various the kernel has so many facilities, or load a module, that would also be a system call. Now I want to stress here that you have a program written in Python, you have a program written in Go, a program written in C, and you have different, like in Python you have read file, in Golang you might have like IOUtil read file. You have the shell, right? You might have shell scripts. Well, when you open and read stuff from a file, all these different languages end up doing the exact same thing. They will always end up doing a system call somehow. Otherwise, you can't really open or read a file. So you can take a program written in an unknown language, right? Or just a binary that you have no idea of the source code. But observing at the system call layer, you get a pretty good idea of what the program intends to do, even if it's a completely bizarre and unknown programming language to you, or if a compiled program. Now here I am listing both on Windows and Unix known system calls. Okay, it's a pretty useful thing, and you see they're not that much different, right? So we talked about fork here, exit, another system call, or wait for another program to finish, and the same kind of functionality with different words existing on Windows too, right? In case you want to do, instead of fork, you do create process. Right? I said it might have slightly different semantics, but the end result is the same. Or dealing with files, again, very similar. IO control, IOCTL, or read and write here on devices. This time, again, similar functions on the Windows side. Pipes, like when you create a pipe on the shell, again, that's a system call that actually connects these two programs. Or shared memory, we talk about shared memory, and the map, again, very similar things on Windows. And again, for changing the permissions on a file, that's also a system call, right? You would do chmod system call, or changing the owner, chown system call. And again, here on Windows. So all this, you can get that information by observing the stracer output of a program. And you can go on this video that you have and see how that looks like. Now, we can start also thinking of how to get the whole memory of a program out. Well, we said that in Unix everything is a file, and for that reason, even the running memory of a program can be represented by a file. Until recently, you could go under the /proc file system, which is a fantastic file system. I'm urging you to look more into the /proc file system, because it is a running state of processes on the system, accessible as a file system. You can cd to it ls and cd to a PID. Let's say you have a process with a PID 33. You can cd /proc/33 and then ls, and you will see a file called mem that has all the memory of that program, right? Or there might be a CTL file that you can control, by echoing kill in there, or echoing, something you can kill the process just by writing something in the file. And so that is definitely, I would have to say here that on recent versions of Linux, they've made it a bit harder to actually get the data out of that mem file. And of course, you need to be the owner of the running program to be able to access that part of the file system. Otherwise, it would completely break security there. But also, another thing you can do is like just debug the process as it's running live. So you can connect your debugger, and we'll be using GDB for this session. You can connect to the running process. Again, that is happening also through a system call called ptrace, that you start to trace a process. And you can, for example, make the process dump its memory contents to the disk. Well, if you manage to make it dump its running contents to the disk at a place that you control the file system, then you just have access to the memory contents of a process that maybe you did not own, right? If you have managed to do that. So yeah, it is pretty subtle that the now file system permission will control that part, that data that was before controlled by a running process that belonged to another user. There are many other ways that you can actually get memory and have it present to us in a file. On the right here, I'm showing you what's called core memory. So these are magnetic cores here, and what was happening is like by setting some voltage on these wires, you can make these cores, these magnetic cores, being magnetized either one way, like going, for example, up this way, or down this way. So that would be in 1 or 0, and you can see here from how many of these guys are in one line, you can imagine how many bits of information, probably 8, right, here. So 8 times whatever, like this can be a 64 byte, for example, core memory that you can store 64 bytes. And in the beginning of computers, memory was actually implemented like that. Now, when we extract memory, though, and especially when we extract memory from a big program or the kernel, or something, we are altering the state of the system. So when we're extracting, for example, kernel memory, and we're writing on the file system, well, there are big parts of the kernel that have memory that relates to the actual state of the file system. So if we're writing on the file system while we're extracting memory, you can imagine that this might completely mess up the quality of our data there. Now, to address that, when we extract memory from a system, we should really try to not touch the system as much as possible. So we could pipe it directly to the network. Of course, again, if we're creating network packets, we are messing with the state of the network stack of the kernel as we extract it. Or we could write on a USB stack, right? Then we're messing with the state of the USB subsystem on the kernel. But other parts of memory will probably be copied fine. Like, for example, the audio part of the kernel might not be affected by writing to either the USB or the network. Now, to do that, we have a video over here where you can see a command called netcat, which is like cat, but over the network. So when you cut a file, you can concatenate two files together. With this command, you can concatenate two remote files together, or a local file to a remote file, and essentially sending data very easily from one computer to another. See this video for how to use netcat. Now, we're going to deal in the linked video here with debugging. It's going to be a short, let's say, demo of GDB and process debugging. I have created this program for you called Hello Secrets, which just has a store of of secrets. Like it asks you for a secret and then you type it, but it doesn't echo it back. Right? It changes the terminal echo property so that when you type, nothing is typed back. So the user can actually type a secret, and that's persisted in memory, and can tell you how many secrets it knows already. Well, but you as a user in front of the computer cannot see the secret because it was never echoed back in the console. Well, using the techniques that we just talked about, we're going to be able to extract secrets from this program. And please go to this video and check it out. In the next video, we're going to talk about extracting system memory from the whole system. Thanks, guys.